Let us estimate a population median. We'll now use the bootstrap method to estimate an unknown population median. In this case, we're going to use a data set called BIRDS, which is basically a data that includes the baby weights and the number of days that mothers were pregnant. In this table, we have the variables for mother-baby pairs. The birth of the baby and the number of days the mother was pregnant, the mother's age, the mother's height, pregnancy weight, and whether or not the mother was a smoker during pregnancy. So let us take a look at the table here. Let's take a look at the first three rows. Birth weight, the number of days that the mother was pregnant, the age of the mother, height, and so on. Birth weight is an important factor in the health of a newborn infant. Smaller babies tend to need more medical care in their first days than larger newborns. So it's going to be helpful to have an estimate of birth weight before the baby is born. One way to do this is to examine the relationship between birth weight and the number of days that the mother was pregnant. Well, a simple measure of this relationship is the ratio of birth weight to the number of gestational days. The table ratios contains the first two columns of baby as well as the column of the ratios. The first entry in the column was calculated as below. 120 divided by 284 days, which is approximately give us 42.25%. So that's how we calculate these ratios. A simple division helps us to calculate the ratios. This is basically what we see in the ratio. Birth weight, the number of days that the mother was pregnant, and the ratio. 120 divided by 284, 113 divided by 282, and so on. Let's take a look at the histogram of the ratios as well. Visualization, always a good method to analyze the behavior of the data. Let's take a look at our histogram. What do we see here? On the horizontal line, we basically have the ratio, and on the vertical line, you have the percent per unit. So the center seems to be around here. 0.45 seems to be the ratio. So at first glance, the histogram looks quite symmetric. With the density at its maximum over the interval of 40% per day to 45% per day, but a closer look reveals that some of the ratios were quite large by comparison. The maximum value of the ratio was just over 78%, almost double the typical value. Let us sort this descending order. So we have a better analysis of the data. .38% is quite large. The median gives a sense of typical ratio because it is unaffected by the very large or very small ratios. The median ratio in the sample is about 42.90%. So if we look at the percentile using percentile function and passing 50, the 50th percentile is the median, as you remember. We see it is about 42.91%. But the question is, what was the median in the population itself? We need to estimate that. We don't have the actual population median. Our method will be exactly the same as what they did for San Francisco compensation and salary. We will bootstrap the sample 5,000 times, resulting in 5,000 estimates of the median. Our 95% confidence interval will be the middle 95% of all of our estimates. So let us begin the process. Let us construct a bootstrap confidence interval. We'll start by defining a function that we call one bootstrap median. What does it do? It basically bootstrap the sample and return 1, the median ratio in the bootstrap sample. Let's define our function, resample the ratios of the samples, and returns the median. Feel free to run the following line of code. And please note that you're going to get different values than what you see here, because this is just resampling. If I run this line of code, I get 43%. Now we can use a for loop to generate 5,000 bootstrapped medians. As you saw before, we're going to generate medians from 5,000 bootstrap samples. The number of repetition is 5,000, and we're defining a for loop. We're going to define the endpoint on the left, on the right, so we can capture the true population parameter, which in this case is the median. The 95% confidence interval goes from about 42.55% to 43.27%. So we're estimating the median birth weight to gestational days ratio in the population, which is somewhere in the interval 42.50% and 43.30%. The estimate of 42.90% based on the original sample happens to be halfway in between the two endpoints. It's not true all the time, so don't assume this is a fact. This just happens in this scenario. To visualize our results, let us draw the empirical histogram of our bootstrapped medians and place the confidence interval on the horizontal axis. Let us resample the medians and then create a histogram. What is the distribution of resampled medians? This is our histogram. This histogram and interval is similar to those we draw in previous section. The big difference here is there is no green dot showing where the parameter is. We don't know where that dot should be or whether it's basically even in the interval, right? We just have an interval of estimate. It is a 95% confidence interval of estimate because the process that generates it produces a good interval around 95% of the time. Please keep in mind that this interval is an approximate 95% confidence interval. There are many approximations involved in its computation. The approximation is not bad, but it is not exact. Estimating a population average. So far we just saw how to estimate the median of the population. We can do the same process for averages and the means. Suppose we want to estimate the average age of mothers in the population. A natural estimate is the average age of the mothers in the sample. Here's the distribution of their ages and their average age with 27.2 years. Let's take a look at the histogram. Remember to visualize your data all the time to get some sense of distribution of the data. As you can see, the data seems to be skewed to the right-hand side. Let us find the average. The maternal age average is about 27 years, which happens to be around here. But what was the average age of the mothers in the population itself? We don't know the value of this parameter yet. Let's estimate the unknown population parameter, which in this case, population mean, using the bootstrap method. To do this, we'll adopt the code from bootstrap median to instead define the function bootstrap mean. The codes are the same, except that the statistics right now is the mean, that is the average, instead of the median. So they collect the means in an array called bootstrap means instead of bootstrap medians. Let us run the following function and repeat this process 5,000 times using a for loop. Let us define the endpoints because we are creating confidence interval. We need to know if the true population is in the confidence interval or not. So on the left side, you have 26.91, and on the right-hand side, you have 27.56 years old. The 95% confidence interval goes from about 26.9 years to about 27.6 years. That is, we are estimating that the average age of the mothers in the population is somewhere in the interval 26.9 years to 27.6 years. Notice how close the two ends are to the average of about 27.2 years in the original sample. The sample size is very large. We have 1,174 mothers. And so the sample averages don't vary much. We're going to explore this observation further in the next chapter. The empirical histogram of 5,000 bootstrapped mean ages is shown below, along with a 95% confidence interval for the population mean age. So we use the bootstrapping method and our histogram. is visualized down here. Once again, the average of the original sample, which is 27.23 years, is close to the center of the interval. That's not very surprising because each bootstrap sample is drawn from that same original sample. The averages of the bootstrap samples are about symmetrically distributed on either side of the average of the sample. Notice also that the empirical histogram of the resampled means has a roughly symmetric bell-shaped, even though the histogram of the sampled ages was not symmetric at all. Let's take a look at the maternal age histogram. This is what we had before. And as you remember, it had a tail toward the right-hand side. This is a consequence of the central limit theorem of probability and statistic. Later on, we're going to see that what the theorem says. We basically talked about central limit theorem about 2-3 chapters before, but we're going to go over it again. Now let us talk about an 80% confidence interval. We can use different confidence levels to estimate and construct a confidence interval. You can use the bootstrap sample means to construct an interval of any level of confidence. For example, suppose you want to construct the 80% confidence interval for the mean age in the population. You would take the middle 80% of the resampled means, so you would want 10% of the distribution in each of the two tails, and so the endpoints would be the 10th and 90th percentile of the resampled means. So you can define the left endpoint and the right endpoint as the 10th percentile and 90th percentile. The left endpoint and right endpoint are going to be different now. If we take a look at the histogram, as you can see, now the yellow line shows the confidence interval. This 80% confidence interval is much shorter than the 95% confidence interval. It only goes from about 27 years to about 27.4 years. While that's a tight setup estimate, you know that this process only produces a good interval about 80% of the time. For estimating a population proportion, as you remember, the population parameter can be mean, median, it can be proportion, it can be variance. So in the sample, 39% of mothers smoked during pregnancy. Now we're jumping into the population proportion. We're interested in finding the proportion now. So if we run the line of code, in maternal smokers, if the value, the Boolean value is true, it means that the mother smoked during pregnancy. And if you divide it by the number of births, it's going to be about 40%. Remembering that a proportion is an average of zeros and ones, the proportion of mothers who smoked could also be calculated using array operations as follows. In the maternal smoker, count the number of smoking and divide it by the length of the column. You get the same number, 39%, or about 40%. So the question is, what percent of mothers in the population actually smoke during pregnancy? This is an unknown parameter. We don't have that piece of information. We can estimate it by bootstrap confidence interval. The steps are analogous to what we did before for median and the mean. In a process that is now familiar, we'll start by defining a function, one bootstrap proportion, that bootstraps the sample and returns the proportion of smokers in the bootstrap sample. Then we'll call the function multiple times using a for loop and get the 2.5th percentile and 97.5th percentile of the bootstrap proportions. So let's see, what do we have? Let's define our function as usual. And generate the proportion from 5,000 bootstrap samples by repeating 5,000 times using a for loop. They're going to define the endpoints of the 95% confidence interval. And it generates the following confidence interval for us: 36.29% and 41.91%. So the confidence interval goes from about 36% to 42%. We can resample the proportions and visualize what we have. So as you can see, the confidence interval is the yellow line on the horizontal axis. Here in using the bootstrap percentile method. The bootstrap is an elegant and powerful method. It's important to keep some points in mind before using that. Make sure to start with a large random sample. If you don't, the method might not work. Its success is based on the large random samples, and so resamples from the sample resembling the population that way. The law of averages say that this is likely to be true provided the random sample is large enough. To approximate the probability distribution of a statistic, it's a good idea to replicate the resampling process and the procedure as many times as possible. A few thousand replications will result in decent approximations to the distribution of sample median, especially if the distribution of population has one peak and is fairly symmetric. As you saw before, we used 5,000 replications in our examples, but recommend 10,000 in general. The bootstrap percentile method works well for estimating the population median or mean based on large random sample. However, it has limitations, as do all methods of estimations. For example, it is not expected to do well in the following situations. If the goal is to estimate the minimum or maximum value in the population for a very low or very high percentile, or parameters that are greatly influenced by rare elements of the population. The probability distribution of the statistic is not roughly bell-shaped. The original sample is very small, say less than 10 or 15. Now, in using the confidence intervals,